DiSalle is going to talk about absolute space and Newton's theory of relativity.
Thank you. It's a pleasure to be back here. I was one of Howard Stein's students, and I continue to be. I apologize if you've heard some version of this talk before. Those of you who have will corroborate me when I say that on previous occasions it's fallen like a 100,000 kilogram lead balloon. In relation to, a lot of this work is inspired by Howard's work on Newtonian space-time, and it's really remarkable to me that after 50 years, to me it seems there's still so much to be learned about Newton's views of space and time, and also about the nature of our knowledge of space and time from Howard's work, and guided by Howard's work from new research into Newton. It's also very startling to look back and to see how much of what one is doing now was anticipated by Howard in some way or another. In fact, I often look back and I find there's something in a footnote that I thought I had thought of myself, but actually I must have read it 30 years ago when I first read Howard's papers, kind of in the position of a kind of backwards John the Baptist, the prophet of one mightier than I who's already been here. But as I said, I think being guided by Howard's approach is helpful not only for understanding Newton and not only the nature of space and time, but also these broader issues of instrumentalism and realism, and the relation between those and empiricism that one finds in questions about Newton's theory of space and time. Now, of course, the paper that we are now, in a way, celebrating the 50th anniversary of is a hugely influential paper in one respect, because it's taken to be a huge contribution to a controversy on the nature of space and time, a metaphysical controversy that's been going on about since the early 18th century, and that, in a sense, took on new life because of Howard's work, which was regarded, and I think is still regarded, as a very serious and surprising and insightful contribution to one side of that debate. All of that's true as a sociological remark. I think, in a sense, it's mistaken philosophically because, not that his paper should have been less influential, but I don't think we've paid enough attention to what he was trying to tell us. I think he tried to warn us against seeing Newton's work on space and time as defined in the terms of that controversy over the metaphysics of space and time that we've been caught up with for the past 50 years. And I think what he was trying to tell us was that Newton was doing something very different from making metaphysical arguments on one side of a classic metaphysical debate. What he was trying to do was, as Howard put it back then, analyze the empirical content of a set of theoretical notions. My interpretation of that, at least, is that he was suggesting that what Newton was really doing was contributing something to how we can understand theoretical claims about the nature of space and time. How we can understand theoretical claims about the spatio-temporal structure of the physical world, and how through these we can understand the nature of motion and force. We know that the theory of absolute space is a theory that we don't agree with anymore. We think it was really the wrong theory for Newton's physics, and we have very good reasons to think that. On the other hand, I think it makes sense to think of the theory not only from the point of view of people who look at it from a point of view from which it's outmoded, but even from Newton's point of view, as an instrument. This is not to say that I think Newton was an instrumentalist regarding space and time, but I think he regarded the theory of absolute space and time as an instrument. And I think it was Howard Stein who was the first person I ever heard say, and possibly still the only one, that when we think about science as an instrument, or we think of science as from the point of view of an instrumentalist, the question we really have to clear up is, what is it an instrument for? And you can appreciate the instrumental value of science by treating that question as a little bit more subtle one than asking, how is a scientific theory useful to us in prediction and control of nature? You can ask, well, what, as an instrument for helping us understand the nature of physical interactions, that's the purpose for which Newton constructed his theory of absolute space and absolute time. It was an instrument by which he was enabled to understand physical interactions of a kind that had never been thought of before. George has already prepared the way for this discussion in a lot of ways. Another way of putting that, I think, would be to say that Newton's theory of space and time frames questions about the nature of physical interaction. It's a framework within which he develops a theory of interaction that's quite unprecedented. But this is what I think is the striking thing that I've learned in the past few years of talking with this about George. Newton's theory of absolute space is a framework within which he develops a theory of interaction that is thoroughly relativistic. And part of my argument today is that was really the point of his developing the theory of absolute space. Because one thing that I didn't realize 10 years ago, I would say, when I first started talking to George about this, the theory of universal gravitation definitely has a history that we've heard something about. The theory of absolute space also has a history. And the two histories are really deeply intertwined. In fact, this is the thing I didn't realize before. One has grown up in sort of thinking about the absolute relational controversy with the notion that there are these texts of Newton's like De Graaf and then the Principia, and they form clues to a kind of whole fabric of thought that lies behind them. And what I've learned over the past 10 years, especially, again, from talking to George, is, this is something that just suddenly struck me 10 years ago. De Graaf was written from a radically different point of view. De Graaf is the beginning of a history of which the theory of absolute space is the culmination, at least as far as space and time are concerned. And a radical transformation in Newton's view took place during that time. And that transformation consists in his coming to understand what I call the Newtonian theory of relativity. I'll explain exactly what I mean by that, because I do exactly mean something by that. But this is, I've often thought, it's not solely my decision, I've often thought that if this book that we'd like to dedicate to Howard gets off the ground, this quote from Howard should be the motto. And the famous quote from Newton, of course, how to collect the true motions from their causes, effects, and apparent differences, and conversely from the motions, whether true or apparent, from their causes and effects, shall be explained more fully in the sequel, for to this end I have composed the following treatise. And Howard Stein wrote 50 years ago, the notion that the Principia was composed in order to explain how to determine absolute motion has been rejected by some with shocked and fervent rhetoric. He was referring in particular to Hans Reichenbach, who regarded it as an incredibly naive remark that reflected how little Newton as a philosopher understood what Newton as a physicist had accomplished. But it seems to me that one does well, in a case like this, to read the book. To see whether it does what the author says he intends it to do. There's a couple of interesting things packed into that. I think Stein was convinced on what, thanks to the work of Craig Fox, I'm even more convinced now than I was at the time I first heard the stories from Howard. But Reichenbach actually didn't read the book, but only read the Scholium. And the other thing is that it means something in particular that in order to understand what Newton, he's telling you, in order to understand what he means by absolute and relative motion, you actually have to see how the theory is applied. I hope to show you that the history of this is interesting and illuminating. First I'm going to go back to the question, what do I actually mean by a theory of relativity? I mean by a theory of relativity something like what one means when one says that Einstein came up with the theory of relativity. You just have to accept that there's more than one theory of relativity, and that one of them came long before Einstein. And I particularly want to distinguish it from a mere philosophical commitment to relativity, which I take to be defined by these characteristics: a conviction on grounds of epistemology or metaphysics, or both, but not particularly physics, that motion is and can be nothing but the observable changes of relations among bodies, that the idea of privileged states of motion and motion with respect to space are scientifically and philosophically just inherently illegitimate notions, and that space and time are philosophically suspect theoretical entities based on an illegitimate inference to the best explanation. I think that's what most committed relativists and relationalists have believed, or at least that's some of what they believe, at least since the time of Leibniz. So this is a well-known quote from Leibniz. I don't think it's necessary to read it all, but I'll just, the important point about it is two things. One is that there's something sort of contradictory about it. If motion, or rather moving force, is something real, as it seems we must acknowledge in Leibniz's metaphysics, motive force is something real, then it must have a subject. Now here's the relativist part. If A and B move toward each other, all the phenomena will be the same, no matter to which we attribute movement or rest. And if there were 1,000 bodies, I still agree that the phenomena would not furnish us, or even the angels, any infallible reason for determining the subject or the degree of motion. Each one may be conceived as at rest, and I believe this is all that you demand. But you will not deny, I believe, that each body truly has a certain degree of movement, or if you wish, force, notwithstanding the equivalence of hypotheses. I don't read this just to bash Leibniz. If anyone wants to read Leibniz being thoroughly bashed, you can read the footnotes to Howard Stein's 1977 paper on the philosophical prehistory of general relativity. But this is another really relevant part of Leibniz's relativist view. This is one that was really, in a sense, more relevant to Newton, because not that he would have read this, but he would have known this view intimately from other people. We speak as the situation requires in accordance with the more appropriate and simpler explanation of the phenomena. It's just in this sense that we use the motion of the primum mobile in spherical astronomy, while in the theoretical study of the planets, we ought to use the Copernican hypothesis. As an immediate consequence of this view, those disputes conducted with such force and with such enthusiasm completely disappear. For even though force is something real and absolute, motion belongs among phenomena and relations. We must seek truth not so much in the phenomena as in their causes. Now the reason why, again, I don't want to talk about how inconsistent Leibniz was about that, lots of people defend him on that, and I hope they have a fine day for it. But when I say Newton had a theory of relativity, what I mean by that is that Newton thought it was really fundamentally important for our understanding of forces and causes to be reconciled with our picture of relativity. Once Newton grasped the idea of relativity thoroughly, I don't know when he did this, but once he grasped it to the point that he started articulating it in treatises on motion, he took it upon himself to go through the process of conceptual revision in order to make the theory into a consistent theoretical whole. Which is why I would say, when I say a theory of relativity, I would say that these three aspects apply equally to Einstein's theory and to Newton. We have an account from the laws of physics of fundamental theoretical magnitudes, the ones that actually matter in physical interactions. And they're physical measures, they're empirical measures. That's what makes them meaningful theoretical magnitudes for Newton. And by means of that, we have a principled distinction between what are the invariant physical features of a system and those that just depend on your point of view. And we have a critical analysis of familiar concepts that already exist either in the scientific discourse or in everyday life that reveals the extent to which they represent a sort of partial or perspectival version of something that we understand more deeply. We understand the unifying essence of from physics. So when I say Newton's theory of relativity, I mean he had a theoretical point of view from which he thought it was really important for the concepts that Leibniz refers to, like force and cause, to be reconciled with the principle of relativity. I think the only other person in his time who was doing anything like this was Huygens. It's hard to understand the extent to which he was doing that because almost all of it, aside from a statement of the relativity principle, is in unpublished manuscripts. So as far as sort of public presentation was going, Newton was the only one for a long time trying to articulate a theory of relativity. And my claim is the theory of absolute space was introduced at the point in time that it was, the notion of absolute space, precisely in order to frame this theory of relativity, because it isn't in use before. I don't want to say that there was never anything in Newton's thought that corresponded that was like what he called absolute space later. This is a quote from his paper on the laws of motion, apparently from the 1660s, saying that there is a uniform extension or space or expansion continued every way without bounds. All bodies move about in it, etc., etc. It's not necessary, I think, to read the whole thing. This isn't really that different from what he says about absolute space later. But he didn't use the phrase absolute space. In one sense, that's not important, because, after all, it's just a new name for the same thing. On the other hand, it tells you that when he started introducing the phrase absolute space, he did it for a very particular reason. He didn't do it because he found it existing in the literature. The distinction between absolute motion and relative motion was a very commonly made one. And the general distinction between absolute and relative quantities was something that was standard. But not the phrase absolute space. And I mean, I really would love for anyone to correct me on this, but I don't know of anyone who ever just said that. The only discussion of space being absolute that comes before the manuscripts immediately leading up to the Principia is in De Graaf, where he says space is not an absolute thing, because he claims in De Graaf that space is an emanative effect of existing things. I don't really want to go into that either. But that leads me to my point, which is that in De Graaf, if this is right, then it might be one thing that I ever noticed about Newton that I got to tell Howard Stein that he didn't already know. But that's just the definition of absolute space in the Principia, which I just put there. Well, now I remember why I put that there. Okay, so I don't have to read the first part of it, but this is the part that's relevant. Entire and absolute motions can be no otherwise determined than by immovable places. For that reason, I did before refer those absolute motions to immovable places, but relative ones to movable places. Now, no other places are immovable, but those that from infinity to infinity retain all the same given positions to one another, and upon this account must ever remain unmoved, and do thereby constitute immovable space. So we tend usually to think, well, this was Newton's metaphysics of space, so then he also realized through corollary 5 of the Principia that two of these frameworks, as he described in this, when he was discussing absolute space, a set of immovable places that retain the same position to one another from infinity to infinity. Two of them that are relatively in uniform motion are physically equivalent. That's essentially what corollary 5 tells you. So the usual picture we have is, well, he basically believed in absolute space. I'm not denying that. And he thought of corollary 5, and he never really figured out how to reconcile the two. I think that a better view of the situation is he thought of absolute space when he realized that it was important to explain how motion and relative spaces work. That's when he introduced the distinction between absolute and relative space in the first place, when he was trying to articulate the theory of relativity. So, for example, what time did I start?
Going on for 21 minutes.
Okay. I think I moved a little faster. Let me go back to De Graaf then. I mean, the thing I realized about De Graaf for the first time approximately 10 years ago, it was clearly written before Newton had developed an understanding of the relativity of motion. In fact, I realized that from De Graaf, one could learn a sort of historical technique for dating manuscripts by the extent of Newton's understanding of the relativity principle. Now, this is a very famous argument. Well, I'll skip that one. Let me just say, let me just summarize. De Graaf says some things that Newton also says in the Principia. Right? He says that even according to Cartesians, bodies revolving around other bodies suffer from centrifugal forces. And he says this is a distinction between revolving and uniform motion that the Cartesians implicitly accept, but philosophically deny. And so he says something like this, kind of angrily in De Graaf. What is this tendency that bodies have to receive from the axis of the rotation of their vortex? What then? Is it to be derived from the true and philosophic rest, according to Descartes, or from their ordinary and non-philosophic motion? In the Principia, he says, he makes the same argument. But here he says, he does it more subtly. And he says, in their system, in other words, the Cartesians, who suppose that our heavens, revolving below the sphere of the fixed stars, carry the planets along with them, the several parts of those heavens, which are indeed relatively at rest, do yet really move, for they change their position with respect to one another, which never happens to bodies truly at rest, and being carried together with their heavens, partake of their motions, and as parts of revolving wholes endeavor to recede from the axis of their motion. But then there's another argument from De Graaf that doesn't have a counterpart in the Principia, and this is something that Howard Stein brought up 50 years ago, that Descartes' definition of motion in the philosophical sense, as motion relative to contiguous bodies, essentially makes a hash of the first law of motion, the principle of inertia, or even Descartes' first law of motion, often mistakenly identified as the principle of inertia. No one can assign the place, according to Descartes, at which the body was at the beginning of the accomplished motion, or rather he has not said whence it is possible a body will be moved. And the reason is that according to Descartes, it's not possible to define and assign the place except from the position of the surrounding bodies. And that after any motion has been accomplished, the position of the surrounding bodies remains no more the same as it was before. For example, if the place of the planet Jupiter were where it was the year before, then having been accomplished, it would be at rest. By what reasoning, I ask, will the philosopher Descartes describe it? It follows that Cartesian motion is not motion. It has no velocity, no definition. There is no space or distance traversed by it. So, hence, it is necessary that the definition of places Hence, the local motion be referred to some motionless thing, such as extension alone, or space, insofar as it is seen to be truly distinct from body. Now, there isn't a counterpart to that in the Principia. Howard Stein expressed his regret that Newton didn't make this argument public, and there would have been a fruitful discussion. I think that's true. On the other hand, I feel that I understand why he didn't make it public, because it refers to the need to refer motion to immobile places, which, by the time he wrote the Principia, Newton no longer believed. It's true that he believed in a conceptual framework in which the only true motion that a body has is its motion relative to absolute space. But in physics, there isn't any need to refer any motion to absolute space. So, but that's not the only sense in which the de Grave represents a kind of pre-relativistic view. This is, in a way, a more interesting sense, because this is the thing that I said you could sort of track through Newton's manuscripts to put them in the right order, so to speak. This was what told me, in particular, that de Grave is long before the drafts of the Principia that they all begin with the phrase de motu. He has these three things that he defines: conatus, or endeavor, right? Resisted force insofar as it is resisted. Impetus is force insofar as it is impressed on something. Inertia is the internal force of a body so that its state should not be easily changed by an external force. He still has a sort of medieval view that these are three different things. Well, whether it's a medieval view or not, it's not a relativistic view. But at some point, Newton grasped this. So this paper, this draft on the motion of spherical bodies and fluids, one of the earliest drafts called de motu, if not the earliest, I'm forgetting now, but there's a list on George's hand. This is where he first gives what we now call the Galilean relativity principle. In the Principia it became a corollary, but here it's a basic assumption. Law number 3, the motions of bodies within a given space are the same among themselves, whether that space rests or moves perpetually and uniformly in a right line without any circular motion. And law 4, by the mutual actions between bodies, their common center of gravity does not change its state of motion or rest. And this scholium, I think, explicates the sense in which he's gone beyond the point of view that he was expressing in de Grave. The whole space of the planetary heavens either rests, as is commonly believed, or moves uniformly in a straight line. Hence, the communal center of gravity of the planets by law 4 either rests or moves along with it. In both cases by law 3, the relative motions of the planets are the same. Their common center of gravity rests in relation to the whole space, and so can be taken for the still center of the whole planetary system. Hence, the Copernican system is proved a priori, for the common center of gravity is calculated, if the common center of gravity is calculated for any position of the planets, it either falls in the body of the sun or will always be very close to it. I think this is interesting for a lot of reasons. I consider this the first articulation of the notion of inertial frame, in a sense, in a kind of, I think, however they would say, in a Pickwickian sense, because Newton is still thinking of frames moving in absolute space. But the point is, I mean, Huygens unquestionably came before Newton in articulating, he was the first person to at least say in print what we now call the principle of inertia, and what we now call the Galilean relativity principle. And it's possible, if not probable, that Newton got these ideas from seeing Huygens' papers at the Royal Society. But the idea of an inertial frame, in the sense that the whole planetary system can be regarded from differently moving points of view, and that the solution to the problem of the solar system is independent of which of those frames you articulate it in, that is a radically new idea. It's an application of Huygens' idea. Huygens may have thought of it. I don't want to take any credit from him, especially since I haven't really read everything he wrote in his marginal notes and notebooks. And there's so much more there than I've got to look at. But the point is, this is one of the things that I refer to as the theory of relativity, realizing that the whole problem of planetary motion has to be understood in a different light. That the question of finding out what's at rest in absolute space isn't really relevant. You have to find a relative space in which you can find the center of gravity of the system, and then you will have solved the problem of the planetary system. You will have solved it a priori, by which, of course, he obviously doesn't mean without empirical evidence, because he's talking about calculating the center of gravity, which requires empirical evidence. I think he means a priori, as opposed to by giving a kind of plausible conjecture based on your conception of what the causes of the motions might be. Of the kind that Leibniz talked about when he said, well, when we think about causes, it might make more sense to be a Copernican. Newton here is arguing, well, it's not a question of a plausible conjecture. There's a solution to this problem. And it doesn't require you to know whether the relative space in which you find this solution is at rest or in uniform motion. Now, it's just after this, in this paper called On the Motion of Bodies in Regularly Yielding Media, that Newton introduces the ideas of absolute space and time. He gives you definitions of them. The reason why this looks like this, I kind of I left these in because the little upside down carrots, or whatever you call those, indicate places where Newton inserted something. There are deletions too. I'm only showing you this to give you a sense that he was actually working through these definitions and correcting them. There's nothing really in these definitions of absolute space and time nothing significant that you don't find in Principia, right? All things are located in time as the order of succession, and in space as the order of position, etc. And then there's this definition of relative space, that which is considered immobile with respect to any other sensible thing, such as the space of our air with respect to the Earth. These spaces, however, are in fact distinguished from one another by the descent of heavy bodies, which in absolute space seek the center directly, but rotating absolutely are deflected to the side. In a relative space, rotating absolutely are deflected to the side. So he's developed the whole theory of absolute space at the same time he's realized that there's an equivalence class of relative spaces, which he still thinks of as within absolute space. It's not clear what alternative he could have come up with. I think one of the things one can say in his defense was it was another 200 years before anybody actually tried to spell out this theory without thinking of it as in the background of absolute space. Now, that's not really an excuse, but many other smart people viewed it the way he did. But this is an interesting remark that he makes. The aim of explicating all these at length is that the reader can be freed from certain common prejudices and imbued with clear and distinct conceptions of mechanical principles may agree to what follows. Moreover, to sharply and diligently distinguish absolute and relative quantities from one another, this is really literal translation from Latin. It's been necessary, since all the phenomena depend on the absolute, yet ordinary people do not know how to abstract thought from sensible appearances, always speak of the relative. So much so that it would be absurd for either wise men or even prophets to speak of them otherwise. Now, this is an early version of what appeared in the Principia, where he talks about those who interpret the relative motions mentioned in the Bible for absolute motions strain the sacred writing. So he's saying we can't use the Bible to argue against modern physics because you're interpreting what's said there as if it meant absolute motion when it only means relative. I'll come back to why that's important. this explication of the definition. This definition should be considered in relation to the definitions of inertia in the graph. The internal, innate, and essential force of a body is the power by which it perseveres in its state of rest or uniform motion in a right line. It's proportional to the quantity of the body. It's truly exercised in proportion to the change of state, and insofar as it is exercised, may be said to be the exercised force of the body. Now he says, the force of a body arising from its motion is that by which the body endeavors to preserve the total quantity of its motion. It is commonly called impetus. So he's taken a massive step toward relativity, but not the final step, which is in De Motu Corporum, I think the last draft before the Principia. This is more or less the way it runs in the Principia, although I have that on another slide if anyone wants to look at it. But here he says something that's, from a relativistic point of view, makes sense in a way that the previous definition doesn't. The innate force is the power of resisting whereby each body, insofar as in it lies, perseveres in its state of resting or moving uniformly straight forward. It is furthermore proportional to the body, nor does it differ at all from the inertia of the body of the mass other than in our manner of conceiving it. The body, in fact, exerts this force only during a change of its state affected by the impress of another force upon it. It's either resistance or impetus, which are distinct only in relation to one another. George read this definition before, but I think it's important to see this in context. Resistance is commonly attributed to bodies at rest, impetus to those in motion, but motion and rest are distinct only in relation to each other, nor do those things truly rest which are commonly regarded as being at rest. Now this is a fundamental change. A body exerts this force only during a change of its state affected by the impress of another force upon it. Because up to that time, he and everybody else, and long past that time, everybody else, or almost everybody else, went on thinking that there's this power that maintains a body in motion, that it acts all the time to keep a moving body moving. And now he's clearly understood that from a relativistic point of view, it acts only when another body interacts with the body. That's a fundamental change. I'm not the first person to notice that. Harival, for example, in his introduction to these manuscripts, noted that already. I'm sure George, of course, didn't need me to tell him that. So I don't have to read this because it's just a slightly reworked version of the version we just read, but this is the one that appears in the Principia as definition 3. I'll just say one thing about it. He says here, the inherent force may be called by the very significant name of vis inertiae, or force of inactivity. Now, a lot of people throughout the history of science have regarded this as a sign of deep confusion on Newton's part. I think he was the only one who understood inertia clearly. He gave it this funny-sounding name and called it a significant name because he thought it drew attention to its peculiar character as something that appears either as a power, if you regard a power to move other bodies, if you take the frame of reference in which the body is moving, or a power of merely passively resisting if you take the frame of reference in which the body is at rest. And I think that's what he was clearly trying to say, because there's no way to reconcile the theory that he was confused about the force of inertia with how clear he is about its relativistic character. So that's almost word for word what was in the previous draft. So the culmination of this is corollary 5 and the Galilean principle as we know it from the Principia. Then there's the additional corollary 6, which functions, at least in Newton's view, as a kind of quasi-relativity principle, indicating that the motions of bodies in a given space are the same among themselves, even if a force is acting on that system, provided that the force is acting equally and in parallel lines on all the bodies in the system. Now, why would he think of this? I think this is an interesting, I'll I'll answer that in a moment. I just want to mention this explication of the definitions that it sounds like the one that I read a few slides back that comes at the end of those definitions in the definitions of absolute space-time and all of that in the paper on the motion of bodies in regularly yielding media. This is a really familiar quote, I hope. But there are certain really interesting aspects of it. The first thing you should notice about it is this comes before he talks about space and time. Here he says, I've laid down the definitions of such words as are less known and explicated the sense in which I would have them to be understood in the following discourse. Absolute space and time are not discussed in the following discourse. There is no claim in the Principia to be able to know the absolute motion of any particular thing. He says, I do not define time, space, place, and motion as they're too well known to all. So he no longer thinks of, what he thinks that he had to define was the theoretical apparatus of the Principia, which he did in definitions 1 through 8. It's not necessary to give definitions of absolute space and time here. Of course, there's a long discussion of it which is the famous Scullion that we all love to hate. Now, getting back to this remark about Corollary 6, I don't know how much I have to add to what George said about it, other than its place in this history. This is the application of this George already read. There's just a couple of things about it that he didn't mention. One is, the whole point of this remark in Newton's Liber Secundus is to say that we can talk about forces in systems even if those systems are taken to be falling with respect to other systems. He's saying our analysis of the forces acting within a system of bodies is robust in spite of any hypothesis you might have of how this system is moving in absolute space. That's why he says, even if the whole solar system is being impelled in some direction by some external force, my argument about where the force acting on Jupiter is directed still holds. The other interesting thing about it is, again, its place in the history. If you didn't see it by now, I think you can see, just by understanding this aspect of Jupiter, that he's able to treat it as a system falling in the system of the sun. He's able to treat it as if it were at rest. That's a very different view of what's going on than what he says, what must be sometime earlier in De Graaf, when he says, well, if we can't plot the position of Jupiter with respect to absolute space as some immobile frame, then we have no hope of applying the laws of motion. Here he's saying, well, the whole point of applying the laws of motion is that we should be able to analyze a system of bodies and to determine the extent to which it's acted upon by an outside force, if there are differential forces acting within it that cannot be traced to the interaction of the bodies among themselves. And it's absolutely crucial to the whole physical picture now, that we should be able to understand such a system of bodies as being in its own local frame of reference, to treat it, as George put it, as a quasi-insular system. He already talked enough about Proposition 3. I don't have to do that. Proposition 3 is one of the places where George uses Corollary 6. Sorry. Newton. Did I say George? Isaac's brother, George Newton. A natural mistake. Just like I'm always calling Kant Michael. Anyway, what is this corollary, what is this proposition about? It's about how you consider the forces, the accelerated forces acting on a system of bodies, and how you distinguish them, how you distinguish the forces acting on the whole system from the ones acting within it. But that's a really interesting problem, because it leads Newton to this argument about how to think of a system as revolving around a center. Right? Because the equable description of areas indicates that a center is respected by that force, by which the body is most affected, and by which it's drawn back from its rectilinear motion, and retained in its orbit, why may we not be allowed in the following discourse to use the equable description of areas as an indication of a center about which all circular motion is performed in free spaces? In other words, he's saying this, knowing how to distinguish locally acting forces from globally acting forces is part of what allows us to think we've solved the problem of the structure of a system as an isolated system, to find out what is the center around which it revolves. This is the key to being able to use this whole apparatus to come up with a relativistic solution to the problem of motion in the solar system, and to answer the Copernican question. How much time do I have? I have 45 minutes? I've used 45 minutes. Okay. I'll skip that part. Pictures are nice. I'll just go to, this just tells you, yeah, Howard already thought of all this. So what am I doing here? And I was going to tell you this too, but I'm just going to skip to the end. That my reading of Newton's view of the relativistic character of physics and the importance of this changing conception of inertia is not just the view of someone born in the late 20th century. It was acknowledged by a contemporary of Newton's, namely Berkeley, who saw it in exactly the same way. The real essence of his argument against absolute space was that Newton didn't need it because he has a relativistic theory, as his conception of inertia shows you. So anyway, I'll conclude then. This is a quote that George already read, so I don't have to read it. When he says, this whole conception of the constitutional frame of nature was developed by Newton at the same time as he was discovering the law of gravitation. In a sense, my talk is complementary to George's, I hope, because this is the other half of this metaphysics of nature, that is the picture of space and time. The picture of space and time is not something that was solidified at the time of the de Graaf and then partially spelled out in the Principia. It was something that was evolving, and a key factor in its evolution was Newton's development of a theory of relativity. The other key factor was his understanding of this long-range force of nature. When Newton says, I wish we could derive the rest of the phenomena of nature by the same reasoning from mechanical principles, for I am induced by many reasons to suspect that they may all depend on certain forces by which the particles of bodies by some causes hitherto unknown, etc., etc. Everyone has probably heard Howard say this. It was one of his favorite quotes. I don't know if I have something to say about it that he didn't think of, but there's something that at least I only recently came to understand what it means. I hope the principles here laid down will afford some light either to this or to some truer method of philosophy. This bears on the question of instrumentalism and realism that I mentioned at the outset. Because I was always confused by the word method. I always assumed that he meant the same thing here when he talks about methodology, the experimental method. But he's actually thinking of the whole theoretical apparatus of the Principia. That's the method being referred to. What is the method? Well, as Howard would say, it's a method inseparable from a metaphysics. The metaphysics of nature is that against this background of space and time, there are forces of interaction. Luckily, even though we can't discern the background of space and time, we've come to understand that these interactions have a kind of relativistic aspect because the laws of motion have an inherent relativity principle. this method of philosophy is a method for determining what the causal interactions in nature are. What are the forces of nature? And so the sort of realist aspect of this is that I've used this framework to discover forces of nature, that there are other forces of nature that are out there to be discovered. And if someone comes up with a completely different framework, it will mean that mine wasn't quite correct, but it will add to this picture of the forces of nature. And that if you think of absolute space and time as not, I'm not saying, again, it's not something he actually believed in, but he actually is seeing it as part of the method for investigating nature. And in that sense, it functions as an instrument, even if in the long run, it's wrong as a metaphysics. Thank you.